to climate change in mountains. And the interesting thing which you need to think about is all the people talk about is average temperature changes. And I would argue that that's not that important. What is more important is, when do you worry about water? When it's too hot or too cold or too wet or too dry? This is really when we start to worry. This don't mean anything. As I mentioned before, my definition of average is your head is in the oven, your feet is in the refrigerator, and your belly button is average. So let's look at what is happening in mountains globally first. This is the latest, and it's up to September this year. This is the CO2 in Hawaii, which is the best observation we have. And you can see it has been increasing at a very steady rate in spite of all the virus. So even since the virus has disrupted all the transportation, we still are on the track, because remember, CO2 stays in the atmosphere for at least 400 or 500 years. The other thing you need to remember is methane. Methane is increasing very rapidly, and that's a really nasty greenhouse gas. It doesn't last as long as the CO2, but it is increasing very rapidly because we have a lot of ruminant animals. We use a lot, we generate a lot of methane from oil and gas extractions, and now we have a lot of problems in the Arctic.
I have a question.
Yeah. Yeah, go ahead.
Please go ahead.
What's your question? No? Okay. Shall I go on?
Yes.
Okay. So we have a lot of problems now in the Arctic, in Russia and in Canada, because the Arctic is melting fast and all the wetlands in the Arctic are actually generating methane. So when you look at the methane graph, you can see it's accelerating quite dramatically. So what I'm going to do is I'm going to show you lots of graphs, and my wife always tells me you have too many graphs, so bear with me. So one way you can look at climate change is you look at the time series versus, let's say, precipitation, so you can see a trend. You can also do this kind of stuff, where this is typically how we classify students. These are the dumb students, and these are the very bright students, and you are probably all up in that category, and this is the mean. So this is how we mark exams, right? We look at the mean in the population, and we look at the really good ones and really bad ones. Well, we could do this with temperature, where these are the low temperatures per year and the high temperatures per year and so on. So I'm going to show you a number of graphs like this. And then I'm going to show you graphs like this, where this is the temperature axis and this is the precipitation axis. So if a dot, which represents 1 year, let's say the year with temperature and precipitation, but if the dot is up here, it's cold and wet. It's down here, it's cold and dry. If it's up here, it's hot and wet. And if it's down here, it's hot and dry. So that gives you a bit of an idea on how these different things happen. So if you look at the northern and southern hemisphere, the northern hemisphere is in red and the southern hemisphere is in blue. Over the last 100 years or so, the average temperatures have increased by about 1.3 degrees. And remember, the Paris Accord is telling you we should try to keep the temperatures below 1.5, which we will never be able to do, but we'll still try, and we're still hopeful to keep it at 2. So this is the global average. If you look at a mountain country like Switzerland, you can see that their increases are about 1.5 to 2 degrees. And then when you have one of the few mountain stations and you look at what has happened, like this one in Switzerland, which is at 2,500 meters, they have increased over the 100 years by about 2.5%, which is already much higher than the global average. So this gives you a little bit of an idea that the mountains are actually warming up far faster than the lowland. And here is the picture of North America. This is Canada. Here's the border. And I'm going to show you lots of stuff from the Rocky Mountain areas here. And it is now clear that Canada is one of the countries which is warming up the fastest. So if you look at the annual increases in Canada, it's been about 1.7 degrees. The winters have actually increased faster than the summer. And if you look at the Arctic has actually increased even further. And the mountains where I live, they have increased much faster than the rest of Canada. And this is temperature changes, and this is precipitation changes. Now, the precipitation changes show you a very complicated picture, because I don't think we see a very good trend, because in the rest of Canada, we have had increases in precipitation. However, in the mountains, we have had some increases and some decreases. So keep in mind, precipitation is very hard to predict in mountains. So basically, if you look at this today, Canada is actually increasing faster than the global average in blue, or the Canadian average. So the mountains are really increasing. So when you look at the evidence we have now, the Northern Hemisphere is increasing by 1.3 degrees, Switzerland about 2 degrees, the high mountains about 2.5, the Canadian mountains close to 2, and the Arctic about 2.3. So not only do we have enough data now from high mountain stations, but we also have recreated the temperature changes by drilling into mountain lakes, looking at the sediments and looking at the organisms in the sediment. And we have been able to recreate that temperatures in mountains are warming up faster. This is bad news, okay? So the assumption has always been that if you look at temperature from low to high per year, you get a bell-shaped curve. This is the average temperature per year, and this is the extreme cold and the extreme hot. So in the past, everybody told you, well, it's getting warmer, so there is a shift from the blue to the red, which means we're going to have less cold and more hot conditions. That's been the basic assumption, but now things have actually changed. And the reason why they have changed is we have gone from this to this because we're getting more extreme conditions, which means we're going to have more low and more high extreme events, which means this whole graph is being shifted. The mean is still the same, but the frequency is different. And so if you put this into the new concept of this is what we did in the past, this is what we do now, which means we will still get some cold events, but much less frequent. But we will get much more hot and dry events in the future. And this has happened in Canada in the last 2 years. We still got some horrible winters for a short period of time, and obviously we have much more dry and hot conditions. I can prove this to you by looking at the different records on a decade basis. Each one is a decade down here. The red is the record hot temperatures, and the blue are the record low temperatures. And you can see in the 1930s, when they had this huge drought in North America, the hot temperatures exceeded the the low temperatures quite a bit. But look at what has happened since about 1980. The hot temperatures are increasing, and the cold temperatures are decreasing, but they're still present. So we still get extreme winters, not just hot summers. So this is the example of 2003 and 2010 in Europe, where they plotted the summer temperatures and showing you when these extreme events happened. So in 2003, we were down here, and in 2010, we are up here. So you can see we're exceeding these extreme events quite a bit. The similar thing has happened in Russia in 2011, I think, 2010, where they had these really hot temperatures. You can see how extreme the temperatures were in that year. So if you look at the extreme events which have happened in mountains, it is quite astounding what has happened in some places. I'm showing you now the picture of a storm in Boulder, Colorado at 1100 meters elevation. They got a rainstorm. These are the days, September 9th, 10th, 11th, and so on. This is the amount of precipitation they got per day. And so in September 2012, they got 230 millimeters in one day. If you look at this in the cumulative event from 1 day, 2 days, 3 days, 4 days, in 4 days, they got 367 millimeters in 1 day. The blue is a 100-year record. This is the amount of precipitation in September which these areas have received, and this is the 2013 event. You can see how much crazy this is, totally out of proportion of anything we have ever experienced. And the blue ones are just the annual precipitation that had such an impact that even affected the annual precipitation. So this is a storm event, which is an extreme event. Let me show what happened a few days ago. In the same place, they had 37 degrees in September, in August. No, September, end of August. End of August, that's a really hot summer. And then within 4 days, they went from 37 degrees to -1 and snow. All within 4 days. Here's the temperature on a daily basis from midnight to midday to night to midday to night. So in 1 day, they went from 33 degrees to -1 and had snow. Incredible events are happening in these mountains. And this is really when things happening. So if you look at the number of climate stations with record temperatures in the last 5 years, from 2015 to now, you can see in 2015, we had about 400 events, the number of stations which had record temperatures. And if you look at the number of stations which were above 40 degrees, you can see what has happened in last year. And this year, it looks like we're either the second or the hottest year on record, depending on what's happening in the next few months. So in 2015, it was the third highest temperature. In 16 was the highest. In 17, the fourth highest. In 18, the fifth highest. And 19, the second highest. So you can see these things are happening at an incredible fast rate. These are the highest temperatures ever recorded in different stations in different countries, again from 2015 to now. And you can see it doesn't matter what country you're looking at, almost every country has experienced different record temperatures. The ones in brown are those which exceeded 50 degrees. Have you ever been in an environment where you had 50 degrees? Remember what your blood temperature is? About 39 degrees? 50 degrees is such a high temperature that if you do not have air conditioning, you cannot function. Keep that in mind. And this is very important for mountains because the mountains are usually cooler, which means we have some opportunities there for adapting. So I showed you this, but I'm going to focus as an example. I'm going to show you the Columbia Basin, which is located in the Rocky Mountains over here. And I'm going to show you what has happened in the last 5 or 10 years in our part of the mountains, which is very similar to many other mountain areas. So here's the Columbia Basin. It is a very large river basin. It originates in Canada and goes all the way, the river goes all the way down to Oregon into the Pacific Ocean. The Canadian part is only 15% of the river basin, but generates about 40% of all the water because it's all mountains. This is a total mountain environment. The Canadian portion has very few people, only about 150,000, and only about 20 communities, and they're very small communities. Economic activity, forestry, hydropower, and recreation. Very little agriculture. So let's see what has happened in this part of the mountains of this river basin. I had the opportunity to work with Alan Hamlet, and Alan Hamlet did some interesting experiments. He used 10 of the global models. He used the European model, the Australian model, the Canadian model, the US model. He used 10 models. And he projected the temperatures, which is that part of the graph. He projected the temperatures based on the recorded record and then projected it to 2100. So if you look at this, this is the range of what the models are telling us. So there is about a difference of about 2 degrees between the different models. Some models have different assumptions, but they all are going in the same direction. And there is a spread, of course, by 2100 of about 3 degrees or 4 degrees, something like that. But let's look at what the precipitation projections are. So this is the record observation, and this is the modeled projection. So some of the models for the same area are telling you we're going to get a 25% increase, and some models are telling us, no, we're getting a 20% decrease. This is a 45% uncertainty. How do you go to politicians and tell them how to predict precipitation when you have that kind of uncertainty? I don't think we can predict precipitation in mountains with any confidence because there's so many aspect and topographic differences that I am not certain we can be really certain about that. And this is problematic for us because politicians and decision makers, they want straight answers. They don't want uncertainty. For precipitation, we can be reasonably confident. For temperature, we can be reasonably comfortable, but for precipitation, we cannot. So here is this Canadian part of the watershed. And what I did is I looked at 10 climate stations. All of these are the climate stations. And then I looked at 18 river stations. These are all the ones in red. These are hydrometric stations in the mountains, which measure how much water is flowing through. So of the 10 climate stations, 6 of them had a 100-year record. The other ones had a 50-year record. So this is the basis which I used for my analysis. So the first thing you need to know is we measure extreme minimum, mean minimum, mean maximum, and extreme maximum temperatures. This is the picture of the January temperatures in one of the climate stations. And this is totally clear to you that over 100 years, the extreme maximum temperatures have not increased very much. But look at what has happened to extreme minimum. The extreme minimum is hugely variable, but it has increased far faster than the maximum temperatures. So it's really the minimum temperatures we need to worry about, not the maximum temperatures. If you plot that up with 6 stations from November, December, January, and so on, you can see all of them showed the highest increase up to about 6 degrees in the winter time, January, February, March. That's when the highest change happened in the minimum temperatures. And also then, of course, in the summer, we get that same thing. So if you look at the mean daily maximum temperatures, they went up about 3 degrees, and each station is slightly different, but the winter minimum temperatures have increased dramatically. And once these temperatures get close to zero, then we're going to have a massive change in shifting snow to rain. And that's going to be important. So keep that in mind. Low temperatures, the minimum temperatures are increasing faster than the high temperatures. Is the variability increasing? I don't need to give you any numbers. You just look at this graph and you look at the variability each year. And of course, in March and April, the variability in our part has increased dramatically. Look at the fluctuation from year to year. And look at this. This is the precipitation in August, in the August period from April to August. Look at the variability has increased, so we have a lot more uncertainty to deal with. This is really problematic because look at these. We had, in the last few years, we had tremendous low precipitation in the summer in these mountains. This is probably the most interesting one. In June, we had this incredible event. So this is a 100-year record from 1913 to now. And this is the monthly precipitation. So the 100-year record was in 1963, about 100 millimeters or so. Look at what has happened up here in 2012, 2015, 2005. We had 3 events which were between 30 and 70% higher than anything we have experienced in 100 years. And this is, of course, resulted in some dramatic storm events which flooded one of the towns. So let me just show you the temperature on a monthly basis. This is for June, the June temperatures, and this is the precipitation. And each one represents a year, a June in 1 year. In 2015, we had the hottest and one of the driest. In 2012, we had the wettest and one of the coldest. So you can see these events have happened in very recent times at extreme conditions. And this is one town, this is another town. You see, this is very consistent in depending on the micro aspects we have. So if you then translate this from the precipitation, the temperature versus the precipitation, so 2016 was an incredibly hot and very dry April. If you take this into the discharge in the river, you can see that the highest discharge happened in the time when it was the hottest and best. And this is obviously snowmelt related, and this is another town. And so you can see in both of these climate stations, 2016 was extremely dry, yet we had the highest monthly ever recorded in 50 years. So this is in April. If we now move to May, we had 2018, which was a very hot and dry summer. And again, in May, which is still in a mountain environment relatively cold, we had the highest discharge, snow melt related. And then we move to June, and a complete shift in June where we have the coldest and the wettest. And guess what? This was a rain on snow event, or mostly rain event, and it did the highest discharge on the record. And again, this is for the same 2 climate stations and 2 river basins adjacent to the climate station. And you can see the 2012 was by far the highest. So you can see we had extreme events even during times when it was very dry and hot, and when it was very cold and wet. So when you look at this, this is the the Canadian portion of the. This is the summer precipitation for this station and the summer precipitation for this station. You can see on the west side, we have had a dramatic decline in precipitation over the last 10 or so years. If you look at this, the summer precipitation on the east side, you can see there is not that much of a change. So there's huge differences between west and east. Remember, the Pacific Ocean usually brings all the storms into the mountains from this side. And so the lee side usually is very different from the west side. But obviously the pattern has changed, and now we're getting much, much less precipitation. So how do we do this on a regional basis? So remember, I had 10 climate stations and 18 river basin stations. So this is the record monthly temperature of the 10 climate stations with a 100-year record. And this is the months in which that record occurred. And if you look at this, here are the 10 climate stations. In 2015, most of them had the record temperatures in 2015. In April was 16, in May 18, in June 15, 7 and 17. And then even in the fall, in October and November, almost all of these stations had record temperatures. This is the monthly precipitation, and this is much, much more variable, but even here we can see lots of these record precipitation events have actually happened in the last 5 to 10 years. If you then look at river basins and where did the record discharge happen, you can see that February, March, April, May, June, July, September, October, and November, we had record discharge in almost all of these stations. So it's almost every month where we have a huge record impact in this mountain environment. And then I can also show you, we also had very low charge, particularly in June and July in 2015. So in summary, what this is telling us is that in February and March, we had the hottest temperatures, we had the highest discharge because of all the snow melt, and we had record high monthly precipitation in 2012 in the very early part of the spring. And then in the summer, we had the 2015, which was again the hottest, and we had this rainfall event which created all the big storms. So it's all in the last 5 to 10 years where we have experienced these record incidents. The other thing which is interesting is the trend in some places has not been like this. You know, we always look at trend levels and we say, look, here's a trend. What has actually happened is a step change. Until about 2003, you can see the variation has been around here, and all of a sudden it went to a different stage. And I'm not sure exactly why, but there's a number of stations I can show this. And one of the reasons might be that in 1999, we had a major El Nino. And that El Nino pattern might have shifted ocean current to the point where we're in a different phase. I can't prove it, but obviously the data shows you there's a real step change which has happened, and that complicates all our analysis. So changing glaciers, this is a very important part because remember, the glaciers produce the water at the time when you need it most in the summer. And the projections are, this is a picture recreated from a drawing in Switzerland, and this is 2003, and this is what they expect to happen in 2050. And this is based on a 1.8 degree temperature increase. Now we're already at 2, so this is going to be probably even more dramatic. Wuyi, which I know quite well, he does a lot of study in the Andes, and he looked at what is happening to the glaciers in the Andes, and this is showing you the length of the river, the glacier, the length of the glacier advance, and how it has been declining in all of these glaciers. And this is one of the glaciers in Colombia, right at the equator, which we were up 4 years ago. And this glacier is most likely going to disappear within the next 10 to 15 years. The additional problem for this particular glacier is, look at what the geology is like. It's mostly volcanic. And some of these are quite active volcanoes. And every time there's a little bit of an explosion, they deposit ash onto the glacier, and the ash is usually quite colorful, and most of it dark, which changes the albedo, which means the glacier is actually going to melt faster because the dark particles accept more energy, heat energy, and warm up the whole thing. So there's clear evidence that almost all glaciers are melting fast. So remember, this is typically what happens to the discharge in a river that is glacial fed. So usually you got a high in the early summer, you got the snowmelt part, which is up here, and then you get the late summer, which is mostly ice melt. So this is how the river from a glacial fed system is going to change from this type to this type. And so here is an example of one of the glacier fed streams in my part of the mountains. This is what has happened to the temperature, and this is what has happened to the precipitation. So the temperatures have increased, precipitation has decreased. This is in golden, and this is in July, and this is in August. And if you then look at the discharge, you can see that the August discharge is declining. So these glaciers are now at the point where they probably don't produce enough melt. They're small enough that the impact for the August discharge is not very good. So here is another example. The US has one national park called Glacier National Park in Montana. It's a very beautiful park. It was created in 1910. It has lots of beautiful glaciers. Apparently in 1910, it has 25 glaciers. And according to Dan Fagre, my colleague, he did a survey in 2010, and then he said, well, we only have 25 left. And this is just giving you an idea how many visitors go to this park. And it's a glacial park, so most people go to see the glaciers. So by 2017, they had 3 million people visiting that park. And so guess what the advertisement is now? Glacier National Park before the glaciers melt away. They're saying that you should now come and visit the park to come and visit not only a melting glacier, but a dying glacier. This is the new advertisement for tourism. And they will probably have to change the name of the park in probably the next 20 so years, because they won't have any glaciers in the Glacier National Park. That gives you a bit of an idea of the importance of this for tourism. Moving to the Himalayas, the one important thing which the lady yesterday showed is these glacial lake outburst floods called GLOFs. So this picture shows you the main glacier, and this is the tributary glacier, which is much smaller. So the tributary glaciers, they melt much faster than the main glacier, and this is still frozen stuff, right? So because it's all frozen, it creates this nice lake. As this main glacier recedes and the permafrost melts, all of a sudden you get a glacial lake outburst flood, and then this is the kind of thing which happened. Now let's fast forward and see what that means. So this is when the lake was still there, and this is when it happened. This is at the time it happened. And then this is what the river basin looks like after the glacial lake outburst flood. Look at the sediment before and the sediment after. This is going to create so many problems for the next 20, 30, 40 years. Have you ever considered how long it takes for the sediment from the Mount Everest to get down into the Indian Ocean? What is the bedrock on top of Mount Everest? You ever given a thought what the rock is? It's limestone and shale. These are rocks which were ocean deposits, and they were completely uplifted to the top of the mountains. And so they're very fragile kind of rock formations. They create a lot of sediments. And it probably takes decades to maybe centuries for the sediment from this part all the way down to the ocean, because they only move on a kind of a fluctuating basis. They move during big storms to a certain length and get deposited, and then they get resuspended and deposited. So it takes a long time for this to happen. So after GLOFs, we have a huge problem with sediments for all the people who use the water for irrigation, because they have to deal with this kind of thing. No doubt about drought. Yes, we also will have more drought. Here is a quick example of the MurrayDarling. That's the big mountain in Australia, and a big river in Australia from the mountains. And you can see they had all kinds of drought events which are accelerating. And during the 1990, before the big drought happened in the 1990s, this is how much discharge the river generated over the year. And then during the main drought, the river basin was actually growing like this. And then it recovered to some extent, but never recovered to the previous level. And if you have watched the news in December and January this past year, Australia had some of the hottest and the greatest fires ever. And so this gives you a bit of an idea that even if we have a major event, we're never going to go back to what it was before. We might get back to certain amounts, but not to the total. Also, even in my part of the world, if you look at what has happened since 1980s, the red dots are the last 5 years. From 2014 to 2019, See, we're all in the hot and dry part of the situation, so we're going to experience more drought. This is probably the most interesting thing I can show you. These are all the hydrometric stations in the United States. And this is in May 2011. The dark black and blue dots are the stations which were in extreme flood conditions. See, 90% extreme flood. All these stations were in an extraordinary low drought condition. They had virtually very little water. And the Mississippi, which starts up here and goes down here, at the same time had massive floods in the headwaters and complete drought in the lowland. And of course, eventually the drought was mitigated because all this flood eventually brought things down, but it took about a month to more in order for this to happen. So it can happen in a river basin at the same time. I never experienced this before, where you had a river basin where you had a flood and a drought in the same place at the same time. So when we look at floods and droughts, there's a real problem. We can actually predict the floods reasonably if we have good data. Droughts are far difficult to predict because we never know when they start. We never know how long they last, and we never know when they actually quit. So it's easy to actually know, and we get about 24, 48 hours of advance notice when we're going to expect a flood. And the reason for that is it depends on the rainfall and the snow cover. It depends on the snow water equivalent in the snow, and so on and so on. But in terms of yeah, we can look at precipitation and temperatures, but we never know how long this is going to persist. So to be prepared, we actually have these advanced notice where we give people warnings and they have time to move if a fast event occurs. In terms of being prepared for a drought, this is much more problematic because it's a progressive event over time. So keep that in mind. So this is part of the what is happening in my part of the world in terms of indicators of climate change, and keep in mind it is the extreme events which we should worry about, and it is the low temperatures which are increasing faster, and it is the precipitation in mountains which is so erratic that we have very difficulties to actually make predictions. So I'm happy to give you to be open for a few questions, and then we'll take a short break.
Thank you very much, Hans. There is a question for our friend from Albania, and he's invited if you wanted to ask the question directly.
I can't hear him.
Okay, I will read the question. Okay, if I am understanding it correctly, cold and wet weather comes with high discharges of snow. The same with hot and dry weather relating to 2012 and 2015 respectively years, according to the graphs.
Yeah. Why? Well, if you have a lot of snow cover and the spring gets very hot and dry, the snow melts. And if there is a lot of snow water equivalent water in the snow, that can create a flood. So you don't need a precipitation event in order to get a flood. What is even worse is a rain on snow event. And I will show you this later on. If you have a good snow cover and it's cold, if the rain hits that snow cover, you will have surface runoff of the snow, and this can also create a flood. So you don't need a lot of precipitation in the spring when you have lots of snow and you get hot temperatures very fast. Does that help?
I think so. Okay. Oh yeah. Okay. Yes, he is. He thanks for the question, for the answer. Sorry. Other question? You can write it on the chat or ask for. Okay, there is a raised hand from Beatriz Fuentealba. Please.
Yeah, hi, you can hear me?
Yes, a little bit with noise on your in background, but please.
Okay, I want to know a little bit more about glove events and about the sediment problem, because you said that the only way that the sediments could we can stop this problem with sediment is that these sediments flow to the ocean. But you can, I want to know if the vegetation could grow up in the sediments and maybe could stop this problem. I'm asking because I'm living Peru and we have many problems with this kind of events, and I'm trying to think in other way to try to stop this kind of problems. Thanks.
Oh yeah, yes. The sediment can be very beneficial, and if you look at most of the good agricultural areas are in the lowland where the sediment over time has accumulated. But in the mountain part, the sediment is very dynamic. Every year during peak flow, it moves, and it only moves a certain distance. It doesn't go all the way through the system unless you have an incredible extensive storm. But even then, in a main river basin, it would never go from one storm all the way from the top to the ocean. So in the mountains, you probably can't grow very much vegetation in the river basin itself, in the sediment. But in the lowland, that's the best, we're basically exporting soil, more or less, into the lowland. All we have to do in the lowland is add organic matter to the sediment, and then you have the best agricultural area. But in the mountains, that's much more difficult. Are you still surviving? This is a marathon session, so I hope you have a lot of stamina. So if there is no more questions, you all can take a very short break while I switch. And we now say, well, here are all the problems. What are we going to do about it?
Okay. Thanks a lot, Hans. Yes.